Start here with some questions, if you guys have anything from homework or class-related stuff or lecture or whatever. Ava?
Let's go through like number 8 on the homework.
Yeah. Sure. So, if I'm looking at number 8, the directions say find the domain of the function algebraically and to express your answer using interval notation. So when I'm looking for a domain, there's 3 things that I care about when I look in the function. I'm looking for division, I'm looking for a radical, and I'm looking for a logarithm. Now, you guys didn't talk about logs last year. I'm not going to have any logs yet. So really, we're talking about looking for division or radical. If I'm looking at number 8, which is what you asked about, and my pen wants to work, we're gonna try doing this for a minute. So if I'm looking at 8, do I see division? Yes. So if I see division, what I care about is taking the denominator and setting that not equal to 0. Okay with that? All right. And I guess I should ask, do I see any radicals? No. So this is the only thing I have to worry about. So I just need to solve this equation. What kind of an equation do I have here? Well, it's a quadratic because it has an x squared in it. To solve a quadratic equation, what are some of the techniques we can use? You could do the quadratic formula. You could factor, or maybe in some cases you can solve directly. I would probably opt for the solve directly in this case since there's no bx term in my quadratic. Those are good candidates to solve directly. So I'll just add 1 to both sides, square root both sides, and when I square root both sides, what do I have to remember? Plus or minus, and the square root of 1 is just 1, right? Well, now I need to write this as an interval. So I have everything except for 1 and negative 1. And my pen stopped working again. We're doing just fine all morning. Really? Still? I'm sorry. This is driving me nuts. I don't know what's the problem.
Is it the battery?
This battery is like a week old, so it shouldn't be the battery. I just got a new one when it was acting up. All right, well, yeah, do you mind? Thank you, Audrey. I appreciate that. Thank you. All right. So x is not equal to plus or minus 1. If I think about that on the number line, maybe I'm not entirely sure how to write the interval for this. I would draw something like this, right? I'd have not equal to negative 1. would be everything except for -1. And not equal to +1 would be everything except for +1. And what I'm looking for are the overlaps. So I'd have an overlap here, an overlap here, and an overlap there. Do you see what I mean by overlap? So like this arrow, maybe we'll draw these ones in a different color. So this is doing that, right? And then this one is doing that. So what I mean by overlap is like the blue and the green arrows overlap, and they overlap in those 3 locations. Does that? Okay. So my first interval is here. So that's going from -infinity to -1. My second interval is the middle, going from -1 to 1. And my third overlap is the far right, which goes from 1 to +infinity. So that's my domain. Is that okay, Ava? Sure. Yes, Ruth E.
Is the homework quiz like 1 to 22? Like anything from that?
Yeah, that'd be fair.
So it's not going to be something together?
Correct. Correct.
It's not going to be the delta math stuff.
Correct. Correct. Anybody else with homework questions or other things they need to talk about? Cool. Let's get started then. Just let me double check where we left off last time. God bless you. So in section 1.6, we're going to talk about asymptotes. Ordinarily, in your Algebra 2 class, you would have had talked about asymptotes. Obviously, you guys didn't get that far. So we'll just kind of do a brief discussion about what we mean here. So an asymptote is a line that the graph approaches but never touches. So, when we draw one of these asymptotes on our sheet of paper, we usually use a dashed line to indicate that it's an asymptote. So an example of something that has an asymptote, or several asymptotes, I guess, in this situation, would be this function here. that whose graph looks like this. Okay, so again, what we're going to do, if I ask you to find and like verify the asymptotes for this function, is I would start by going to my calculator and graphing this function. So to graph something, I press the y equals button. Just clear out some of this stuff from earlier today. Now this kind of a function here, I would recommend using that fraction command that we've talked about. So I can access that by pressing alpha, y equals, and then choosing that first option. If you didn't use the fraction command, you would have needed a set of parentheses around the entire numerator, and then type the division key, and then a set of parentheses around the entire denominator, which is kind of a hassle. I'm a much bigger fan of using that fraction command, so I can just type it exactly like it looks like on my sheet of paper. Alpha, that's the green one, and then y equals, and then pick the first option. Okay, so once we have that typed in, I don't remember what the last thing I graphed was, so I'm gonna press zoom standard just to put me back in a regular sized window. So this is what my calculator gave me. Is everybody okay with that? You guys get the same thing? Okay. So what I'm going to look for is, it looks like here there's an asymptote. Everybody agree with that? Now that's a vertical asymptote because it's going straight up and down. And it appears that's happening at the vertical line x equals -3. Everybody's okay there? So I'm going to write that down. I also see that this spot looks like a vertical asymptote right here. Right? And that appears to be at the x equals 1. So there's a vertical asymptote at x equals 1. And then there also looks like there's a horizontal asymptote coming through like right here. Did you guys see that? That appears to be at y equals 1. Are you okay with where I'm pulling these numbers from? That I'm just reading them off the x or y axis on my graph? Do you guys see what I'm looking for? Okay. So these are what I believe are the asymptotes based on just looking at the picture. What we're going to do now is confirm that these are actually asymptotes by creating a table of values that are getting closer and closer to some number, and we're going to see. Okay? So let's just show you guys what that's going to look like. So for a vertical asymptote, what I want to do is I want to look at what's happening here as x is getting closer and closer to -3 from the left. So the values of x I'm going to choose is maybe -3.1, -3.01, and then maybe negative 3.001. And I'm also going to worry about where the graph is approaching negative 3 from the right. So that would be like negative 2.9, negative 2.99, and negative 2.999. And usually 3 values is pretty good. Ava?
Can you repeat why you picked the first 3 values?
So I'm looking at this part of the graph that I've highlighted in green. That's the graph approaching negative 3 from the left. So I'm picking numbers that are less than negative 3, but are really close to negative 3 still. Is everybody okay with that idea? Now, if I'm picking these x values, how am I going to get the y coordinate to go with them? If I have an x value, how do I find the y value that goes with it? You have to plug it into the function, right? What does our function look like? Yo, brother, Mr. Kulik, that's going to get pretty messy. Is there an easier way for my calculator to do this for me? Yeah, there's a pretty easy way for our calculator to do that. So since we've already typed our equation into y1, what I'm going to do is I'm going to exit back to the main screen. So press the second button and the mode button. That'll exit you back to the main screen. And then what I'm going to do is I'm going to press the vars button, which is right here below the down arrow. I'm going to go over to the y-vars tab. I'm going to select the function option, and then I'm going to select y1. And now what this is going to allow me to do is use this just like I would function notation. So I can do y1 of negative 3.1. And what my calculator is going to do is plug negative 3.1 in for x for whatever is in the y1 menu. So that's like the y coordinate there. And now rather than having to go through and press all those buttons again to retrieve the y1, I can just press second and the enter button. That'll give me the last thing that I typed. So I can just go back and edit that a little bit to give my next x value. And then I can do it one more time to put in my third x value. And I'm going to take a little break and write down what I see. And what do we notice is happening to the y coordinate here as we're getting closer and closer to negative 3 on the left? Look at those y values. What's happening there? What's that? And by bigger, you really mean smaller because there's a negative sign in front of it, right? They're getting a lot smaller as the closer I get. What value do you suppose that they're heading towards if they just keep getting smaller and smaller and smaller? Negative infinity, right? Is that okay with you guys? Let's see what happens as we approach negative 3 from the right. So I'm going to just second enter, go back and edit what I have. And so I have these 3 values for y as I'm approaching negative 3 from the right. What do I notice about these y values? Yeah, they're approaching positive infinity. To see that something's an asymptote, what I'm hoping the y coordinates do is approach positive or negative infinity. Let's try doing the same thing for x equals 1. So which x values do I want to pick to approach 1 from the left? From below for values that are less than 1. What values would I prospectively pick here? How about those ones? Right? Those are getting closer and closer to 1, and they're all less than 1. Everybody agree? And they're getting like an order of magnitude closer each time, right? And then let's start with values that are bigger than 1. And again, let's get closer and closer to 1 each time. Maybe I'll use those 3 values. What do I see happened here? Kind of the same thing, right? That again, those y values are just getting smaller and smaller and smaller the closer I'm getting to 1. Let's check the other end. Do you guys like using this y1 notation here? Like it sure beats the heck out of trying to type all that stuff in and changing the numbers each time, right? It's a pretty nifty little trick. What do we see there? Oops. So we're getting bigger and bigger each time, heading towards positive infinity. So those were my verticals, right? What if I'm doing a horizontal? What part of my graph am I going to try to be building a table for on my horizontal? I want those parts of the graph. What are the x-coordinates doing at those parts? They're not getting closer and closer to a specific x value, right? They're getting just progressively smaller or progressively bigger. So if I want that left blue circle, I want values of x that are getting progressively smaller and smaller and smaller. So I'm just going to pick -10, -100, and -1000. Now there's nothing special about those 3 numbers. You could have done 6, -254, and -3018. That's fine. I just picked those because they're pretty looking numbers. They're nice and neat and even. But the point is that progressively I'm getting like an order of magnitude bigger. each time, right? And then to get the other blue circle on my graph, I just need positive values. So I'll do that. I'll pick 10, 100, and 1,000. Yes, Bella.
Just to ensure, I have a quick question. I just want to make sure that I did all this right.
Yep.
At the very beginning, when you get negative 3, 1, can you go over how you get those numbers?
I read it from the picture. Remember we graphed it and looked at the picture?
Oh, yeah. So, like, is it the number closest to
So
the
So these guys, like this is where the location of one of my asymptotes, right?
Right.
The vertical lines are defined by an equation x equals. So if I count over on the x-axis, looks like 1, 2, and then going through negative 3 is where that vertical line would be. So that's how I got the negative 3.
Okay.
I did the same thing over here to get the positive 1. And then for the horizontal, it looked like it was this spot here. So that's a horizontal line. So that's defined by y equals. So I just read where that looked like it was crossing on the y-axis, which looked like to be 1.
Okay. Sounds good. Thank you.
Is that okay?
Yeah, I just wanted to make sure. Thank you.
No problem. Notice what happened when I tried doing y1 of 10. What'd I get? Fraction. What would I rather have? Decimal. So the easiest way to fix that is at the end of this computation, I'm going to press the math button and then choose this option 2 that says DEC. That'll ensure that whatever answer it gives you is going to be a decimal. And now, instead of having to type that in at the end every time because I'm going to end up overwriting things, I'm going to press second and the delete button. That allows me just to like insert a number without actually overwriting anything. So I'm going to use that neat little trick here to make that a little bit easier. What do you notice is happening as we're getting smaller and smaller? What value are we approaching? No. We got 0.87, 0.99, and 0.999. Looks like 1, which is what we're expecting to see, right? The y value should be going to 1. And then we'll do the same thing. I'm going to start from the bottom of my table and go up because it's just going to make the button pressing a little less of a hassle. And again, what do I notice that those are going down to? Looks like 1. What do you guys think? Just so to review, what we did is we took our function, we typed it into the calculator, we looked at the picture. We looked at the picture to find our vertical and horizontal asymptotes. We used the x or y axis and just kind of counting to come up with the equation for the x and y intercepts. And then we used our calculator to create a table of values to confirm what it was that we were seeing. Is that okay? Okay. All right. So in 1.7, we're going to be looking at function operations. And there's 4 kind of fundamental function operations that we would start with. So this says to let f and g be functions that have intersecting domains. Then for all values of x in that codomain, that would be the intersection of the 2 domains. That's what we mean by a codomain. We have the following: f of f plus g of x is equal to f of x plus g of x. F minus g of x is f of x minus g of x. F times g of x is f of x times g of x. And f divided by g of x is f of x divided by g of x, provided g of x is non-zero. So let's look at an example here and show you kind of what this definition allows us to do. So if I want to do f plus g of x, my definition above says I can write that as f of x plus g of x. And the problem tells me that f of x is 2x minus 3, and g of x is the square root of x plus 2. Everybody's okay so far? The only thing I'd have left to do from here is to simplify this expression if I can. Now, since the only operations going on here are addition and subtraction, is there any like terms I can combine here? What do you guys think? What could we combine here? Is there anything? Should say no, right? There's nothing to combine. Why can't I combine, say, the minus 3 and the plus 2? one of them's under the square root and the other one isn't. Same thing with the 2x and the x, right? So this is as good as I can do. Oh, Mr. Kulik, that was like a big fat nothing burger, right? Like, I can get down with that. Oops, I don't mean to do that one. Let's do g minus f instead of f minus g. So again, I follow my definition. That should just be g of x minus f of x. It's too noisy out there. Is everybody still okay? All right. So again, I go to my problem, and I know that g of x is square root x plus 2, and f of x is 2x minus 3. Does that look correct so far? What do you guys think? Look good? Does anybody object? I tricked you all. What's wrong with this?
Why is it g minus f up on top of f minus g?
They're just names, so that part's fine. What's the problem with what I wrote there in the red, though? There is a mistake. I did it on purpose.
Would it be the square root of 2x I? Or 2 plus x I?
Nope. Nope, no eyes. Ava?
That 2 is supposed to be negative now? Well, it is negative. Is it supposed to be positive, though?
Nope. Here's the problem. This entire f of x is being subtracted. So I really should have a parenthesis here. And when I have a negative sign in front of a parenthesis, what do I need to do? Distribute that negative sign, right? Does that look familiar as something you remember doing? Yeah. Why do you suppose Mr. Kulik chose this example? It gives me an opportunity to review this commonly made mistake. Does everybody see what the mistake was? Now it's subtle, right? It was just like it should be a plus 3 instead of a minus 3. But like, is it going to be easy to forget to do that? Oh, yeah. What if I have g times g of x? If I go and I look at my definition above, that should just be g of x times g of x. So that's going to be the square root of x plus 2 times the square root of x plus 2. Everybody okay there? Can I multiply those two things together? What do you think? Yeah. What do I get when I multiply them together? Right? Since they're the same thing multiplied together, it just that thing squared, right? Is everybody okay with that? Sure. Again, why can't I just multiply the insides together? I mean, you could have also written like, oops. You Could have also written that, Bella, that would be okay. But you'd have to FOIL that out. You wouldn't get x squared plus 4 or whatever it was you said.
Yeah.
Okay. All right. So this thing in the red that I have, is that as far as I can go? No, what can I still do?
The square and you can take off.
Yeah, the squared can cancel the squared root. So we're just left with x plus 2. Everybody cool? And that's as far as you could go there. So we have this division problem. So just like before, I'll go to my definition and then look at the problem. I know f of x is 2x minus 3 and g of x is square root of x plus 2. So just copy those in. Does that look okay to you guys?
Yeah.
In your geometry class, what did we talk about?
You have a radical.
Yeah, now, is it wrong to have a radical in the bottom, or is it just not what we're going to do? Because this is that's an important distinction, right?
I don't know. I think it's just not what we want to do.
Yeah, that was just not how we were going to write our answer in our geometry class, right? So that is correct. It's still equal, whether we had like 1 over the square root of 2, or we wrote square root 2 over 2. It's the same number if you type them into your calculator. They're both the same value. In your geometry class, you had talked about how we weren't going to leave a radical in the denominator of a fraction. And that's just a convention, right? So what I would say for you guys is in this class, if that radical that's in the denominator has a variable in it, just leave it the way it is. If the radical is only numeric, then let's rationalize. Okay, so the things that you would have rationalized your denominator in your geometry class, we'll continue to do that. Weird things that have like a variable stuck in there, we're going to just leave the way they are. Sound okay to you guys? And again, this is just Mr. Kulik's preference. These aren't wrong. We're just going to talk about what I would expect from you guys is to do the things that in geometry, we'll continue doing them the geometry way. Things that are a little bit more complicated because they might have a variable rattling around inside of the radical, we're just going to leave. Sound good? Okay. All right. There was actually a 5th operation between functions. You would have, I don't know if you guys did talk about it last year or not in your Algebra 2 class. Typically you do. Does anybody maybe remember? It's not something that's come up yet, so I don't know if you got to it or not. Starts with the letter C, if that helps as a hint. No? That operation is called composition. Does that ring a bell? No. Okay, well then this will be new for us. So this definition reads, let f and g be two functions such that the domain of f intersects the range of g. The composition f of g is denoted by this set of symbols here. That's an f, and then like the multiplication dot, but it's empty instead of filled in, and then g, and it's defined as f of g of x. Now let's talk Mr. Kulik things that grind his gears. When you read that set of symbols, I don't want to ever hear anybody read this as the word fog. It's not the letter O in the middle. That's like an empty, a multiplication dot that's not filled in. Okay? Let's be clear. There's no fog in math class. We're not talking about the weather here. Everybody's clear? This is just Mr. Kulik's pet peeves. Okay? But for all of our clarity, we're not going to say fog. The way you read that set of symbols is F compose G. Or that little empty circle is read as the word compose, not fog. Okay? Since we've never done composition before, it sounds like let's look at a couple of examples. All right. So let's say that f of x is the function 2x squared minus 3x, and g of x is the function negative 3x plus 4. And we're asked to do f compose g of x. This is a little bit tricky, seeing it for the first time. So if you want to give me your A-game attention, that might be good. So I'm going to start by just applying the definition for composition that was given above. So f compose g is f of g of x. Everybody good there? And I know that g of x is equal to negative 3x plus 4. That was given to me in the problem. So I'll replace the g of x with the function that it's equal to. And now what do I do when I have like something inside of the parentheses in front of a function like that? If this was like f of 7, what would I do? I'd plug 7 in for x, right? If there was an a in there, what would I do? Plug a in for x. If there's a 3x plus 4 in there, what am I going to do? Plug 3x plus 4 in for x. So I'm going to take this, and everywhere where there's an x, I'm going to replace that x with negative 3x plus 4. So I usually like to write the function with just sets of parentheses instead of x's, and then I'll fill in what goes in place of the x's. Does everybody feel okay with what I did there? Okay. Next thing up, let's just simplify this down. The composition is now over. We did the composition. The rest from here is just going to be like some simplifying, some basic algebra stuff that you would have done in your Algebra 1 and 2 classes. When I'm simplifying, what should I do first? Stuff inside the parentheses. Is there anything to do inside the parentheses? No, right? Because I can't add negative 3x and 4. Okay, what do I do after parentheses? Exponent. Do we see an exponent there? Okay, what do I get when I do negative 3x plus 4 quantity squared? Is that going to give me 9x squared plus 16? No. No, it's not. We do not distribute exponents. What negative 3x plus 4 squared really means is negative 3x plus 4 times negative 3x plus 4. Right? If I do that, what are you going to do? FOIL, right? Now, what am I going to do with that 2 out front? Well, I'm just going to ignore it for now. I'm going to do the foiling, and then I'll distribute the 2 in at the end. This would be my preference, is the way to do it. Is that okay with you guys? And then down on the other piece, I just need to distribute the negative 3 through, right? Everybody's good? We'll combine our like terms there in the middle. And then distribute the 2 through. To give us 18x squared minus 39x, bless you, plus 20. Is everybody okay with that? Notice that this section, the longest part, was all just the simplifying step. The composition was done way before that. The rest of that was all just cleanup. Will the cleanup always be that difficult? No, man, it just depends, you know? Let's do another example. Sound good? What if I wanted to do G compose f of x? Well, wait a minute, Mr. Kulik. I did f compose G up there. Do I just get the same thing? Right? Should I just be able to do that and be done? Nope. Composition is not necessarily commutative. Now, sometimes it could be, but it's not always. By commutative, I mean like addition is commutative, where 2 plus 3 is the same thing as 3 plus 2. Composition doesn't work like that. We actually have to do it. Oh, man. So I'll just start with the definition. I'll go write the function for f of x down. And then now I'm going to plug in that 2x squared minus 3x into the x's for g of x. Well, g of x was negative 3x plus 4. So in place of the x, I'm going to write in that 2x squared minus 3x. Startled me. Notice the simplifying here. Is this going to be harder or easier than the previous one? Way easier, right? All I really need to do is just distribute that -3 through. Mr. Kulik. Thank goodness. What do you guys think so far? Composition, not too bad? Okay, let's do one more example, and then we'll move on to the next thing. Look at this one. F compose F. Can I do that? Sure you can. Is it going to be a pain in the tuchus? Yeah, pretty much. So, oh yeah, I should wait. Mr. Kulik, show your work. Okay, guys, I will. So I'm plugging f of x into f. The rule for f of x was 2x squared minus 3x. So when I plug that into f, every place where there's an x, I'm going to replace that with 2x squared minus 3x. Everybody's cool? And oh, what do I have to do here? I have another FOIL situation, don't I? Yuckarooskies. It's okay, guys. Do you remember the shortcut for foiling those situations? Remember that? Perfect square factoring pattern. I can use that to do my foiling here, where like this is my A and this is my B. So that would be 4x to the fourth minus 2x squared times 3x. So that would be, and then times 2, so 12x to the third. And then b squared is negative 3x times negative 3x. And that saves me a, I don't know, a little bit. And distribute that stuff through. Right? I guess I didn't really need this line if I was going to do that shortcut, huh? I don't know. You can do it either way. Do you guys see what I'm saying with my shortcut? You can argue about how shortcutty it is to yourselves. It's okay if you're like, Mr. Kulik, that's not any easier for me. That's okay. You don't have to do it. Mr. Kulik likes it because he can do stuff like that in his head using that shortcut. But you have to remember it, which is not hard after you've been a math teacher for like 15 years. You mostly memorize all those things that you're like, oh yeah, I remember that when I was a student. After you do it the same thing for 15 years, you usually get pretty good at it. That's why your math teachers always look like they're so good at math. Just that they have way more practice than you do. Imagine if you're a high school student, you took the same class 15 years in a row. Like, how good would you be at that class by the time you're done? Be like, I could teach this. That's what you're doing. That's what being a teacher's like. You're doing the same class 15 years in a row. It's like, well, I'd be really good at it. It's like, yeah, that's why your teachers why they look like they're good at doing stuff. Okay. Composition. Everybody's okay with doing a composition? Not too bad, right? can be a little, the simplifying can be a little annoying, but the actual compositions, not bad. What do we got, like 15 minutes-ish? Yeah, okay. So we mentioned that composition, not commutative, right? That F compose G wasn't the same as G compose F. We saw that in the previous two, or examples A and B from just prior. Sometimes that does work, though. In one situation where it does work, it's actually something very special. That special situation we're going to define right now. No. No, nothing we did today or do today would be on the homework quiz. So I think we said up through 22 in the homework would be fair game. This is like, now we're getting into the stuff in the 30s and 40s here.
We don't look at our homework during the quiz, right?
Correct. We do not look at our homework. Okay, so let f and g be two functions. We say g is the inverse of f, provided that f compose g of x is equal to g compose f of x. That's just now equal to x. So if that's what's going on, we give g a special name, and we use this symbol. We read that symbol as f inverse of x. So let's talk about what this is doing here. So I'm going to draw a function f using a mapping diagram. So let's say that this is our function for f, that f sends 1 to 4, 2 to 6, and 3 to 5. Everybody okay with that? If we have some function f inverse, the ranges for f will be the domain for f inverse, and the domain for f would be the range for f inverse. And what f inverse needs to do is it needs to undo everything that f just did. So what we're saying is that f of f inverse, let's do the other way though. F inverse of f of 1. Well, what did f do to 1? Turned it into 4, right? And what does f inverse of 4 do? Sends it back to 1. So whatever the input was is the output after the composition. Right? If we start with 1 and we do f to it and then we do f inverse to it, we should get 1 back. That the inverse basically undoes everything that f did. Do you guys kind of see what's going on there from the picture? Take a look at f inverse that we drew there in blue. Is that a function? Sure it is, right? If I look at the domain, all the domains go somewhere, right? And each of those domains only goes to one place, so that's a function. Everybody's cool? Let's look at a different example now. Think about this a different way. What if our function f is defined as a set of ordered pairs? So in f, -2 is sent to 4, -1 is sent to 6, 3 is sent to 8, and then 5 is sent to 8. Right? That's what this is really saying. What would I write for that for f inverse then? How would I describe that as a set of ordered pairs? What would the first point need to be? Very good. 4, -2. And then 6, -1. 8, 3. And then 8, 5. What are we doing here to get these points? Just switching the x's and y's, right? Again, f is sending -2 to 4, so f inverse needs to send 4 back to -2, and so on. Look at f inverse. Is that a function? Nope. What's the problem? Yeah. This is basically saying we're taking 8 and sending it to 3, but also sending it to 5. Up here, though, we noticed that f inverse was a function. Probably should write that down. We said it, I didn't write it, though. So it appears that sometimes f inverse is going to be a function and sometimes it's not, right? Great, Mr. Kulik. That's awesome. Just what I wanted to hear. Unpredictable behavior. Well, hold on a second. So there is a way to tell just by using f whether f inverse is a function or not. We'll get to that next time. This feels like a good place to stop. You guys agree? All right. So looking at the homework, you guys should be able to do up through 30. When will that be due, though?
Sunday.
Not this Sunday. Next Sunday.
Me with like every class. So nothing to do this Sunday.
Sure there is. I think 5 through 22 is for Sunday.
I just had a question about the homework.